Hello, everyone. All right, so as always, real life flow script, not the same, quite different, especially so tracker software. Tracker software asking itself to mess it up when we do it. Go backtracking of an object, whereas in flow script, it just knows it because it's programmed. Of course, air resistance is or is not present, although that isn't the main focus of the lab. It is something to consider. And of course, we can to get the same result, whereas if we redid the exact same experiment on Earth, chances are we'd get a different result. So instead, we're going to get a broadly similar trend, but the so the important equations here, just as always, we have our two update formulas as our code. So position update, velocity update, of course. Then our three relevant forces. That is the force of gravity, which is the um, the mass, the uh, gravitational to Earth times the negative y direction, because that, of course, gravity points, but at the same time, tension is going to point the exact opposite way, and depending on how far along we are in the experiment, it will either be equal to the force of gravity or it will be less than equal. There, and then here is the force of air resistance, drag specifically, which again, does play a part, but it isn't the most important. So here's what happens. Here is the test case. It's the Veratium, how you say it, video. Um, see, there's the object falling down. What we can notice is that the y track is what matters, x track, but this y track, see, there's basically no change, and then there is a change, and it's quite a steep change into that. But there's also these little pauses here, um, and then it falls all the way down, so we're done. Our system is the Slinky, everything else around it. Um, so here's the glow script test case. There's the output from the glow script, but as you can see, we have our various principles on this top right end. To our top left, we have the initial conditions, including the mass, which is the general mass of a Slinky is 0.72 kilograms, as well as where it was relative to where we started the axis of tracker software. Additionally, down here is where the drag constant was located. This was fine tuned, but ultimately, as I said earlier, doesn't particularly matter. And then down here, we have our force calculations, tension and gravity. Said they're opposite. Here is our comparison between the various outputs. So in the middle one, we see the same graph as last slide, and we have just a perfectly flat straight line, and then at an angle representing the falling motion of the bottom of the Slinky. It's just, it doesn't start to fall into a certain point and then it falls. And we see a similar trend in the tracker graph. It's just it's not as precise, and you have these little jagged edges. And the positions of the top, they're just the same deal. Once again, you have these slight imperfections from the human error side as well as the other possible source of error. But in general, once again, the same trend, just a mostly flat line without much change. So what does this even mean? So because the Slinky is a spring, and so the tension in it it counteracts gravity. So basically, if you imagine the top of the spring, it's going down, but at the same time, it's pulling the bottom of the Slinky to it, and therefore that force on the bottom that's from the top is going to fight against gravity, and in fact, it is equal to gravity, and therefore the bottom won't move until the top has fully compressed down. And as we can see in this photo here, which is a pretty good illustration of it, the bottom will only start to move once the rest of the Slinky above it has sort of collapsed down on itself, and so the tension is low, because the relaxed length of the Slinky is when it's fully compressed. So the closer it is to being fully compressed, the less um, tension you'll have, less spring force. So here's some what if questions. So if there is no air resistance, because it's a great question, um, I mean, it's gonna go down faster because there's no air resistance to slow it down. But once again, the bottom will still not move until the top has come down on it. A different shaped spring or just a different spring in general, it's gonna act differently according to the geometry of the spring. But regardless, the trend is still the same. The bottom will always lag behind the top. And if you stretch the slinky at the beginning, it's just going to take more time for it to go down and therefore more time um, for the bottom to start moving down. All right, thank you and bye.